Okay, so let's discuss how to use the basic search algorithm to solve those problems we discussed previously. And as we already noted, that these first two problems could be solved with the vanilla basic search algorithm, and it can be done in linear time. Pretty good. So hard to optimize past linear time. I mean, it's practically impossible because on some level you always need linear time to just read in the input, right? So these first two problems we got solved. Next problem. Given a graph G and a node U, compute all the vertices that can reach U such that all V find all V such that U is in their reach. Okay, a little bit more of a tougher problem. How do we do this? There's a very clever little trick. There is a naive solution, right? So what's the naive like brute force solution? Well, the naive brute force solution is for um, I in V, just compute reach I, and then is U in reach I? Yes. Add, or I should say, is V in reach I? Add V to return set. Okay? That's the brute force way. I mean, hey, if you don't want to rewrite the explore out, if you don't want to do anything else, you don't want to think about it, this will work. Right? But maybe we could think about it. Let's think about it. And let's think about it. Let's think about what it means for a graph to be able to reach for U to be able to reach V. For U to be able to reach V, there is a path from U through some intermediate nodes, x1, x2, dot dot dot, xi, then finally to V, right? But if we want if we want V to reach U, one thing we could do is simply reverse these edges, right? If we reverse the edges here, if instead of the edge U to x1, we simply reverse it to be x1 to U, then now, well, this should be dot dot dot, dot dot dot. Then now we have a new graph. This new graph we have is called the reverse graph. And in this new graph, the path that you took to get to V is now reversed, right? So if in the normal graph U could reach V, in the reverse graph V could reach U. So why is that important? Why is that important? Because if we compute the reach of U in the reverse graph, then instead of finding all the components U can reach, instead we are finding all the components that can reach U. So that's what we do. That's how we solve the algorithm. If we just simply compute the reverse graph and then call explore on G reverse, comma U. So in the normal graph, you had, let me write this. In the normal graph, you had a bunch of vertices. Let's call them find all V. V1, V2, V3, and I'm going to do curly arrows to represent a path. that all were able to reach U, right? So running reach on U in the normal graph wouldn't give you these vertices, right? Reach only gives you the vertices that are reachable by you, i.e., the vertices that you could go from U out, right? But if we compute the reverse graph, then we reverse all these paths. V2, V3. We reverse all these paths, and now if we run the Explorer algorithm on U, we will get all these vertices. Make sense? So we can very easily find all the nodes that can reach U by simply computing the reverse graph. And the time to compute the reverse graph is very simple. It's simply M. Make sense? Okay. So, next question. We want to find the strongly connected components of G that contains U. How do we do that? How do we find the strongly connected components in G that contains U? Well, I have some hints. What does it mean for something to be a strongly connected component? For two elements to be in the same strongly connected component, right? For two elements to be in the same strongly connected component. Let's say this is our strongly connected component right here. Oops, let's make that drawing slightly nicer. This is our strongly connected component. And we have a node U and we have a node V. Okay? For two elements to be in the same strongly connected component, we have to have a path from U to V. Squiggly line. We have to have a path from U to V, and we have to have a path from V to U. Right? That's what it means for two elements to be in the same strongly connected component. We need to know all the elements that U can reach, and then we need to know all the elements that can reach U. And then the intersection of those two sets, are all the nodes that U is a part of, that U can reach and that can reach U. Okay? So we have the components we need to do this, right? We simply compute the reach on the original graph of U, and then we compute all the elements, all the nodes that can reach U using the reverse graph. Okay? And the intersection of these two sets gives you the strongly connected component that contains U. Does that make sense? So, therefore, the strongly connected components of GU can be computed with the Explorer algorithm that is run twice. Okay, so since we're just running this Explorer algorithm twice, and 2 is a constant, it gets dropped out of the O notation, and therefore computing the strongly connected component that contains U takes linear time. Okay? So, computing the intersection. This is just a minor thing. Can computing the intersection take linear time? Does it take linear time? Yeah, it takes linear time. I mean, mainly because you could use the visited array. You could use the visited array and then just go through both visited arrays and see the nodes that have been marked as visited in both visited arrays. So they're pretty simple. Okay, so let's look at the strongly connected components Let's look at the strongly connected components of the directed graph we showed earlier. So for instance, we have a particular graph G, and we have the reverse graph. This is G reverse. G reverse. Okay, so what do? We compute the reach. We compute the reach of B, namely we ask explore G comma B, and then we compute the reach of B in the reverse graph, namely we compute the reach of B in the reverse graph, namely we compute explore G reverse comma B. Okay? And then the intersection of these two sets is BEF. And this is the strongly connected component that contains the node B. Pretty simple. And you could verify this visually, right? You could verify this because there are no other elements that are reachable by B that can also reach B. And then you could do this with all the other components. You could do the same process with all the other nodes. You could go through and do the same process with A. You could do the same process with H. You could do the same process with G. And you would get all the strongly connected components that make up the directed graph. So, finally, how fast is this? Well, to compute a strongly connected component that contains B, it is linear time, right? Okay, so we already answered that question. Next question, is G strongly connected? Can we answer, how fast can we answer that question? I mean, pretty fast, right? If we pick an arbitrary vertex and compute the strongly connected component that contains that vertex, all we need to do is just simply measure the size of that strongly connected component. If the size of that strongly connected component is equal to n, then the entire graph is part of the strongly connected component. So if the size of SCC GU is equal to n, then yes, else no. Right? So how fast does this happen? Well, the speed of this, we could do this in exactly an amount of time that we could compute the strongly connected component that contains U, which is linear time. Okay, so checking if G is strongly connected takes linear time. Running time is O to the M plus M. Okay. Last question. What if we wanted to find all the strongly connected components of the graph? What do we do? And I alluded to this earlier. I jumped a gun a little bit. I'm sorry. But what if we want to find all the strongly connected components of G? What do? Well, we could go to every node. We could just go through every node, find the strongly connected component that contains that node, and then remove that strongly connected component from G. Right? So we don't repeat computation, right? In the graph before, BEF are all part of the same strongly connected component. So we could just randomly choose B, compute the strongly connected component, and then remove it. We don't need this. We don't need to, these nodes are not part of any other strongly connected components, right? So they don't need to be part of the graph. So we don't need to leave them in the graph and also choose E and compute their strongly connected component again, and choose F and compute the strongly connected component again, right? We don't need to do that. All we need to really do is find the strongly connected component, and once we do, these nodes are guaranteed not to be part of any other strongly connected component, so we just remove them from the graph and then guess another node, and then find the strongly connected components of that node, and then remove those nodes from the graph. Guess another node, find the strongly connected component, remove those nodes from the graph. Make sense? So, how fast is this? Oh, I already said, why doesn't it? Oh, I already answered this question. So, how fast this is? Well, in the worst case, what's the worst case for this algorithm? I mean, we removed the strongly connected components after every find because we want to save some computing time, right? But in the worst case, all the strongly connected components are exactly one node big, right? If we had, let's just call it a path. We'll just do one A, B, C, D. If we had exactly just a path, then we have 4 strongly connected components. We have the number of strongly connected components is equal to the number of nodes. And in this case, the worst case becomes n times the n times the running time of this function, which is linear. Okay? So in the worst case, we would need polynomial time to compute all the strongly connected components using this brute force algorithm. But the good news is that we can do this. We can find all the strongly connected components of the graph in linear time. And to do that, we will go over what we need to do that in the next lecture. All right. Thanks for sticking by, guys, and I will talk to you next time. Thanks.